Let's go. First thing, take your homework, pass it to the end of the row. That's because I'm going to do the homework in class today, and I don't want you to work on it while I'm doing it. Second thing, today's class is going to be nothing but the homework that you're just handing in, and I'm going to do it the pencil and paper method with graphs with MATLAB, but I'm not going to do the numerical integration today. We're going to stick with this same problem for 2 or 3 weeks more and make it more and more elaborate. So if you're behind, you want to catch up. If you feel like you were floundering, you want to get past that stage. I realize that I did not show you how to do this problem, so it's not typical of some homework you get in high school and college where we show you how to do it and then you do it. This is, you're supposed to be exploring. But none of the things that you had to do for the homework were out of your reach. So in principle, you could all do it, though I realize it was a struggle for some of you, and probably some of you had trouble getting through it. So let's just see how we did on this. Take out your clickers. First, just click in so I know you're here. Take the homeworks and pass them up to the front, from the back row to the front when you have the piles all there. On the left, on this side also, pass them from the back row to the front. Some beautiful pictures here, I see. Okay. How many people got through to a graph of x versus time of the bicycle motion? Yes? No, didn't get that far. Okay, very good. Of those who got to the point of trying to find velocity and position versus time, how many of you did it with calculus, and how many of you did it by adding up numerically? Calculus adding up numerically. And if you did not even try, vote C, D, E. Okay, so that means there's room for learning here, and that's what we're going to work on today. And then you get next week the problem gets harder, but basically it's a lot of the harder part is building on what you could have done this week. So you get more chances to learn how this goes. Okay, so I'm going to jump right into it. I made a set of notes to make sure I wouldn't make algebra mistakes, and then I left the notes at home, so you have to check my algebra. So here's how the situation looks. You're on this bike and you pedal, and what you notice when you're riding a bike is that if the bike is stalled, you can push hard on the pedal. And even if there's no load on the pedal, like the bike is going downhill, you can only pedal so fast. You can only keep up if it's going so fast. So you try to say at your maximum effort. So this whole concept of this bike rider is assuming you're at your maximum effort. And what you notice is that you can only push so hard on the pedal when it's stalled. On the other hand, if the bike is going really fast, you can barely keep up, and when you're barely keeping up, you're not applying any torque to the pedal crank system. And in between there's something, and we assume it's a straight line. And we could characterize a straight line with the slope c, and you can say the slope is m0 over omega f. This is the free spinning angular velocity. This is m0, the stalled torque. And we just assume that there's a straight line here, so we assume that the m as a function of omega is equal to m0 minus c omega. Or we could write that as m0 minus m0 over omega f times omega. So that's the assumption. People who do fancy biomechanics models use a slightly different curve for this. They use one that bends down here a little bit. It's a hyperbola with asymptotes over here. It's called the Hills curve. But we're just going to keep it simple with a straight line for now. So given this curve, how much power are you putting out? Well, to given omega, how much power you're putting out is the product of the omega and the m. So the power you produce is equal to m times omega, which is equal to the area in this in this curve. And the power you can produce is a function of how fast you're pedaling. If the bike is stalled, you're not producing any power because there's no angular velocity. If the bike is spinning very fast as you can keep up, you're not producing any power because the torque is 0. So if you made a plot of the power that you can produce as a function of omega, it's 0 over here, it's 0 over here, and it has some maximum in between. Now, where is that maximum? It seems like sensibly it would be about halfway in the middle. But to check that, what you can say is let's find the peak power. And the peak power is, we want to say, let's look at dp dt and set that equal to 0. What does that mean? We're going to take d by dt of the power. What's the power? It's omega times the moment. What's omega times the moment, or omega times the torque? It's omega times the torque, which is m0 minus c times omega. That's the assumption for how the torque that you can apply depends on the speed that you're applying it. So we're going to set this thing equal to d by dt of this thing equal to 0. What is d by dt of that thing? Well, we can multiply through d by dt of this part is m0, multiply through d by dt of c omega squared is 2c omega, so we have minus 2c omega, so we get omega at this peak, so I'll call this omega peak, is equal to m0 over 2c. But m0 divided by c, well, here's the c. What is this c here? C is equal to m0 over omega f. So m0 over c is omega f, so this is omega f over 2. So that means our peak power here, that's where the derivative of the power with respect to omega curve is equal to 0, is equal to omega free divided by 2, which is intuitively makes sense. It's about halfway between stalled and as fast as you can pedal. And what is the peak power? The peak power in terms of the variables that are given to us, well, peak power is this halfway point over here. So we're at half of omega f, and we're at half of omega of m0. So the peak power is m0 times omega f divided by 4. And if we want to work this the other way around, sorry, that's not, yeah, mf, that's right, the way I wrote it. If we want to work this around in terms of what's given to us and what we're trying to find in this problem, we were given the speed, the angular velocity you can pedal with no load. That's as fast as you can pedal even when you're not pedaling against anything. And we're given the peak power, so from this you can calculate this m0. So we get m0 is equal to the peak power times 4 divided by the speed that you can pedal when you're going as fast as you can. Okay. So this was not an equation that was given to you. It was one you had to infer from thinking about that graph. And I think some of you were able to do this, and most of you probably needed some hints from a friend or from me or someone to do it. Now the next part of the problem is dealing with the gear ratio on the bike. So how do you deal with this bike gears? And we have a few basic principles we can work with. One is that you think of the gear train as being something which conserves energy. It has low friction, so the power in equals the power out. Another thing is that the parts have to work together, so the speeds and angular velocities are linked to each other by chains and gear teeth and radii and things like that. And a third thing is the various parts have to abide by force and moment balance. And you can use all three of these principles to figure out things about the gear train. In particular, if you take any two of the three things I just said, you can figure out the third. I'm going to show you all three, but we only need to do any two of them, and the third one naturally follows. So there's three things we can work on. One is power, and I'll call it power balance. And in terms of this picture over here of the gear train, we have the power into the gear train is the moment times the angular velocity. That's like force times velocity at the pedal. And the power out of the gear train is the velocity of the wheel relative to the bike backwards. So this is getting in the frame of reference of the bike multiplied by the force. And so the power balance for the gear train is that power in equals power out. or power in is this torque that you apply at the pedals is equal to the force times velocity that the bike pushes on the ground backwards in the bike's frame. Or you can write this a different way, which is that omega over v is equal to F over m. So there's a ratio of kinematic quantities, which is the angular velocity of this and the speed of this point. And there's a ratio of mechanics, force-like quantities, which is the torque here and the force here. And the two ratios are equal to each other, only reciprocal. So if this one is going much faster than this one, now there's the quantity faster and slower doesn't really make sense here because in this case the gear ratio has dimensions. But the bigger this is relative to this, the smaller this torque is relative to this force. And that's always the way gear trains work. And if you want to think about it in terms of a lever. The force which is closer to the axis of the lever has smaller velocity. The force which is farther from the axis of the lever has a bigger velocity. But the ratio of the forces, if the lever is going to be balanced, is the reciprocal of that. So the bigger force is closer, the smaller force is farther when the lever is balanced. And all transmissions work like levers do. So if you just think about teeter-totter, it will tell you how all transmissions work. Any questions so far? Who followed the teeter-totter analogy? Quick. Who did not? Want to hear it again? You're on a teeter-totter, and you have a force here and a force here, and they're balanced. If they're balanced, this force is bigger than this force. On the other hand, as the teeter-totter turns, this motion is smaller than this motion. So the ratio of these two velocities is equal to the ratio of these two forces, only reciprocal. That is, the smaller force goes with the bigger velocity, and the bigger force goes with the smaller velocity in a balanced teeter-totter, which is a form of a transmission. And all transmissions are basically teeter-totters in disguise. Now, anybody want more about the teeter-totter analogy? Okay, so moving on, this is power balance. Another way to look at this thing is just look at the geometry, or so-called kinematics. And how does the kinematics work? Well, we have a chain ring back here, which we call a freewheel. The reason it's called a freewheel is, I don't know, somewhere around 1890 they discovered they could put a ratchet on that piece, and so it could run freely when the bicycle was coasting, so that piece is called a freewheel. We've got this front one, which is called the chain reel, which is connected to this pedal thing over here. And we've got a chain connecting these two. And then there's a chain connecting the bottom, but we're not really worried about the chain connected on the bottom. And then we've got the whole wheel of the bike over here like this. Now, how you can figure out what's going on here is we're interested in figuring out this thing we call V, which is the velocity of the tire relative to the bike. We use the fact that the chain is inextensible. And in fact, we use one of the greatest equations of all time, greater than the equation F equals ma or E equals mc squared. It's the Laurie-Anderson equation. When they get a sound system in here, I'll get the song to play for you. It's the famous equation, let x equals x. In this particular case, the velocity of the chain is equal to the velocity of the chain. And in some sense, all equations in all of engineering and all science are the equation x equals x. You take one quantity and think about it two ways and see what it tells you about those two ways of thinking about that same quantity. So the velocity of chain equals the velocity of chain. How can we think about this? Well, on the one hand, we have the radius of the chain wheel multiplied by the omega, which we think of as the input omega, and that's how fast this point is moving. On the other hand, we have the radius of the freewheel here, multiplying by the omega of this whole big wheel. And so we have the radius of the freewheel multiplied by omega of what I'll call the wheel, omega and w, two different letters here. And that tells us that something about the relationship between the omega of the crank, which I just called omega, and omega of the wheel, because they're related by these two radii. So this tells us that omega of the wheel is equal to the radius of the front gear, the radius of the chain ring in the front divided by the radius of the free wheel in the back multiplied by this input angular velocity. So it says how fast does the rear wheel spin? If you've got a big gear in the front, it spins fast. If you've got a big gear in the back, it spins slow. If you've got big in the back, small in the back, it spins really fast. If you've got small in the front and big in the back, it spins slow. And what they call high gears and low gears depends on those ratios. Now we also are interested in the end, how fast the bike is moving, which is the same as how fast the tire is moving relative to the bike. And that's equal to the angular velocity of the wheel multiplied by the radius of the wheel. And the angular velocity of the wheel we just figured out. So this turns into the radius of the wheel times the radius of the chain ring divided by the radius of the free wheel multiplied by the angular velocity. And we define this quantity to be 1 over g, so we call this thing omega over g, where the gear ratio is equal to Rf divided by R of the wheel multiplied by R of the chain ring. And this particular gear ratio is dimensional, it's not dimensionless, because it's converting an angular velocity to a linear velocity. So it has to be a dimension of the length, the reciprocal length, depending on whether you look at the gear ratio or the reciprocal of the gear ratio.
Professor?
Yes, student.
RF.
Yes?
What is RF?
RF is the radius of this gear in the back. It's the radius of that rear gear, which is called the free wheel. Now usually when people talk about bikes, and this is just a bike-specific thing, they don't actually talk about the ratio of the radii of these two chains, because the ratio of the radii is also equal to the ratio of the circumference. But the gear teeth are spaced equally on both gears because they both have to match the holes in the chain. The pitch of the chain, the so-called spacing between the links in the chain, is fixed. So the ratio of the radii is the ratio of the gear teeth. And usually people then talk about the gear ratio on bicycles in terms of the ratio of the circumference or the ratio of the gear teeth. So they have, for example, a 42-13 combination is a combination of 42 teeth up here and 13 back there. And these things come in standard sizes, say 52, 42, and what's the small one? 28? What? 30, 28. Whereas these back ones tend to be smaller, and they range from about 12 to 30, 32. I guess, what's the biggest anybody's seen there?
34.
What?
34.
34 in the back? Okay. For a very low gear, which means this thing has a low velocity in the back. Okay, the third way to look at the gear train is to do a force or moment balance. So we're still working on the gear train, and we can do force and moment. Actually, all we're going to use is moments for this particular gear train. And how does it work is we look at the front chain wheel, which is held on the bike at this place called the crank axle, with forces here. So now I'm going to draw a free body diagram. This one I wouldn't properly call a free body diagram because I didn't cut it all the way free. I didn't show all the forces, and I also have other things in the diagram besides forces. I have the pedals here. I'm going to assume that I can summarize what happens to the pedals with some moment here. And I also have a chain coming off of here, and I'm going to cut the chain and put some tension here. And this thing has some radius, which I'm calling the radius of the chain wheel. And if I take for this thing that the sum of moments relative to the center here, I'll call that center O, is equal to 0. We use, again, the principle of the teeter-totter, but only the statics part of it. We don't worry about the motion part of it. And we have that moments have to balance. So this radius of the chain wheel multiplied by this tension in the chain has to equal the supplied moment. Now, we can remember what we've got over here. We can draw a free body diagram, not just of the so-called chain wheel or the chain wheel crank system, but of the rear wheel. I'll get you in a second. And we can figure out things about the rear wheel as well. Yes, what's the question? What does this little symbol here mean?
No, vector O. Wait, what do you call back? Zero. Vector O.
Vector O. That's the vector 0. Say again?
To the left. Yeah.
This means this takes the sum of moments relative to point O. So when you have any system, the laws of mechanics apply relative to any reference point, and the sum of moments relative to any reference point equals the rate of change of angular momentum. Basic law of statics, of dynamics. The statics approximation is that we can neglect the inertial terms. It says moments have to balance. So this is using the principle of teeter-totter, where we put the hinge at this middle point, but for the purposes of calculation, you can put it anywhere you want. The middle point is very good because these reaction forces that hold the wheel in place don't contribute to the equation, so it makes the calculation simpler. Yes?
What's in that tension arrow?
What's in that tension arrow? We've taken this part of the bike and we've cut it free from the rest of the universe. And one of the things we had to cut was the chain. We have to fool the chain into thinking it's not been cut, and that's the tension in the chain. Yes?
I have a question about you real quick.
Yeah?
Wouldn't that, if you are would you have some form of units, and isn't a gear ratio not supposed to have units?
Yes and no. This does have units, and yes, commonly gear ratios do not have units, but in this problem we're taking a gear ratio which is relating an angular velocity to a linear velocity, and so we're stuck with units. Who asked the question? You happy with that? So most often you have torque in, torque out, force in, force out, but here we have torque in, force out. So we have angular velocity and linear velocity out, and the gear ratio has units. Okay? Question? Okay, so now let's look at the rear wheel. We draw a free body diagram of the rear wheel, which means we cut it free from the universe. We cut it free from the ground. Here's this force we're interested in. We cut it free from the bike. So there's forces here that hold the wheel in place. There's that free wheel back there, which is part of the rear wheel. There's a bit of chain. We'll cut that chain, and action and reaction says this tension equals that other tension. Or if we don't use action and reaction, we look at force balance in the chain itself, neglect the inertia. The two tensions have to balance for the chain to be in equilibrium. Given this picture here, we have these two radiuses, the radius of the free wheel and also the radius of the wheel itself. And we get from this, by moment balance, the sum of moments equals 0 as a vector equation. In 2D, it's a scalar equation, which is the sum of torques about the origin equals 0. We get that the torque times the radius of this free wheel is equal to the force times this radius of the big wheel, which means we can write the force is equal to the radius of the free wheel divided by the radius of the big wheel multiplied by the chain tension. But the chain tension we already figured out is this moment divided by RC. So we have this is RF divided by R of the wheel, RC times the moment that's applied. So you see that the ratio of the force to the moment is equal to the ratio of the two angular velocities, only reciprocal, just like on the teeter-totter. Why do they have to be reciprocal? Is because power has to be balanced. Where there's a bigger force, there has to be a smaller motion for it to balance the other side. Which is why you can take any two of these equations, 1, 2, and 3, and derive the third. So you can use any two of 1, 2, and 3 to find the third. And so chances are nobody in this room did all three of them. Did anybody here do all three of them? Okay. Especially since I hinted you through doing the geometry and doing the power balance. But the torque balance gives you the same, at least consistent result. Okay, next we want to figure out the whole mechanics of the bike. Bike momentum. So we draw a free body diagram of the bike and the rider. And how does that look? There's the bike. And there's a force holding it up here, and a force holding it up here, and a force pushing it here, and gravity pushing it here. And all we're going to be looking at is F equals ma in the x direction. F equals ma in the y direction tells us things about the support on the wheels, has to balance the gravity. We're not going to worry about that now. So all we're really going to be concerned with is F. So we have linear momentum balance in the x direction. So we better have a sign convention and be clear about what we mean about the x direction. Linear momentum balance in the x direction tells us that F is equal to ma, which I told you all about the philosophy of last time. If you weren't here last time, please watch. Oh, you can't watch the video of that. There is a very good video of last class, but it's an oops video of part of last class, which does not include the philosophy of F equals ma. So ask your friends about F equals ma if you weren't in class last time. What do we have for F equals ma? Well, on the right-hand side, we have m times dv dt. And on the side, we're going to know that v is equal to dx dt if we're going to ever try to find position and not just velocity. But on the left-hand side, we have this force. And this force itself depends on the velocity. Why is that? It's back over here when we were looking at your capacity to pedal. If you're pedaling slow, you can apply big torque. If you're pedaling fast, you can apply high torque. If you're pedaling slow, you can have zero power. If you're pedaling fast, you can have zero power. So this is neither a constant acceleration nor a constant power problem. Now, I tried to warn you around that, but I noticed students working on the problem all fell into the trap of either treating this as a constant force or a constant power problem, which it's not. The power and the force are both changing as the bike accelerates. So we need to get that right over here. The force depends on the velocity. So how does the force depend on the velocity? Well, we know the force depends on the moment by the gear ratio. The way we've set this up is we've said the gear ratio is high when the wheel moves slowly relative to the chain wheel. So the gear ratio showed up as being the force times the moment that was applied. But the moment that was applied depended on m0 minus omega times some constant c. But the omega that was applied depends on the gear ratio and the velocity. And the way we set it up is we said that the omega was equal to the gear ratio multiplied by the velocity of the bike. So we substitute all of these things back into this top equation, and it says that I'm going to switch the sides of it, mv dot, because I like to have the derivative on the left-hand side. And now I'm going to figure out what this force is, but this force is going to be some function of velocity. Some function of velocity which follows from thinking about this curve and thinking about the gear ratio, as explained by all these things over here. So what function of velocity is it? It's, first of all, it's the gear ratio times m0. The bigger the gear ratio, the bigger the reduction, the bigger the force at the rear wheel. The slower the rear wheel goes compared to the chain wheel. And then we have minus this c times omega. But omega itself was g times v. So this turns into g times v. So this part here is omega. Now c itself we can expand in terms of omega 0 over omega f if we want to get back to our original constants. But anyway, we look at this equation. It says that v dot is equal to a minus bv. And a and b are constants we can figure out by cranking our way backwards through these equations. Yes? is G supposed to be squared? Because we have this G from before, so we have a G squared here. Okay, so this is the form of the differential equation. So we're trying to find, this says, how does your acceleration depend on your speed or velocity as you pedal along. And just a little point that I noticed, another problem some of you had in your homework is you're not careful about omegas and W's, and you're not careful about M's and M's. It's nice to keep track capital letters and small letters because there's just not enough letters around for complicated problems. Go ahead, ask your question out loud.
No. It's not a problem. We're discussing it.
It's not a problem, but you're discussing it, but we could all discuss it.
Oh no, we've got the same expression using power is equal to d by dt of half mv squared.
You could use power balance and get the same expression. So there's this intimate relationship between power balance, momentum balance, and kinematics. Just like it applied to the gear train, it also applies to the whole bicycle. That's in problems where energy is not dissipated. If you have friction inside, you cannot use those equations casually. Yes?
You mean that big M is not equal to small m?
I mean that big M is not equal to small m. That's correct. You couldn't see that dash there. I wrote it very, very lightly. In fact, I wrote it in my mind and not on the blackboard. Okay. My apologies for going fast today. I just want to get through this example in one lecture. Okay, any other questions? So now we want to figure out how do we erase blackboards. There's a torque on the eraser from the blackboard friction, which has to be balanced by the grip of the hand on the eraser. But the grip takes a certain squeezing force. Okay, so we want to figure out the solution to this differential equation. How are we going to go about doing that? Well, one way to do it is with the method of guessing. Another way to do it is with separation of variables using straight calculus. Another way to do it is numerically. So I'm not going to do it numerically. I'm not going to do separation of variables. I'm going to do the method of guessing. How does this solution work? Well, you get on the bike and you start pedaling, and you go faster and faster. There's no doubt about that. On the other hand, you're going to not just go infinitely fast. Now, why not? You could say you're not going to go infinitely fast because of friction, but I put no friction in the problem. So we're doing this problem in a vacuum. Okay, in a vacuum with an oxygen tank so you can keep breathing. So you're doing it, you can breathe, but there's no friction, there's no rolling resistance, no air friction, and so on. So there's nothing to stop you from going infinitely fast. So if we were doing a constant power calculation, you would go faster and faster to infinity. If we were doing a constant acceleration problem, you'd go faster and faster to infinity, even faster. Constant power, the acceleration goes down as you go fast because power is force times velocity, so the force goes down as you go faster. But this isn't like that. This is you on a bicycle, and you can only turn the crank so fast. So once you get to the fastest you can turn the cranks, you get to some asymptote. So there is some peak speed here you can get to, and you're going to asymptote to that speed. Now, what is that asymptote? There are a couple ways to think about it. One way is to just be mathy about it and say, I'm going to get to a point where I'm going to no longer be accelerating. Therefore, that's the asymptote. When this is equal to 0, that's when this is equal to 0. So the asymptote is the ratio of A to B. So this height here, which I'll call V0, I can write as A divided by B. But another way to think about it is, what is that asymptote? That's when you're pedaling so fast that you apply no force anymore. That's when you're pedaling at what we call omega F. And how fast is the bike going when you're going at omega F? Well, we just use the gear ratio for that purpose, and that's G times omega F. We said the velocity of the bike is the gear ratio times omega F. Is that right, or do I have reciprocal of that? Let's think about it. I said the gear reduction was G, so this was omega F divided by g. So we know the curve is going to look like this, and it's going to have this asymptote. So we just think, what curves are there that look something like that? Looks like an exponential to me. Looks like a decaying exponential to me. So we can just make the guess that v is equal to, let's say, c minus d e to the minus lambda t. Seems like a reasonable guess. I can't just put e to the minus lambda t because that'll end up at 0. This doesn't end up at 0, so I've got to add some constant to it. And I've got to have some free constants around here to adjust the heights, and I don't really know how fast this is decaying. Is it decaying like this, or is it decaying like this? But the differential equation somehow is going to tell me that, so I take that guess and plug it in. Okay. So when I plug in that guess, and here's where I wish I had my notes so that I would be less inclined to make algebra mistakes, we want to plug in the guess. So the differential equation is that v dot is equal to, and now I'm just going to keep it in this simple form, a minus bv, where we can substitute in those constants later on. And if we want to simplify things, certainly we have, if you check all the constants I did before, you'll find that the ratio of a to b is omega f over g. So we can use that also. So now we want to plug in this guess. So on the right-hand side, we have a minus, and now we have this guess, b times, and where we had v, I stuck in what we think is this function of v is c minus d e to the minus lambda t. So this whole thing is v. And that's supposed to equal v dot. That's the time derivative of this. What's the time derivative of a constant? It's 0. What's the time derivative of e to the minus lambda t? It's minus lambda e to the minus lambda t. So on the left-hand side, we have d lambda e to the minus lambda t. So here's our guess, and the question is this a good guess? Well, it's a good guess if the equation is satisfied. Satisfied means the equal sign feels good. Feels good if things are balanced, left side equals right side. Does the left side equal the right side? Well, it could. Yes?
Shouldn't it be d over lambda?
Why shouldn't it be d over lambda? Because here I have v dot. The time derivative of v is the time derivative of this expression, which is lambda minus lambda times d e to the minus lambda t. There's no integration here. No integration. It's just differentiation. If it was integration, we'd be in trouble because we get stuck doing integrals that we maybe can't do. So this method of checking, at least you can set out doing the method of guessing because you can do the check, because you can always take derivatives. Yes?
Why isn't it negative lambda?
It's not negative lambda because I have two minus signs here that cancel. Other questions? Okay, so this thing has to check out. What do we see? We have of e to the lambda t over here, and we have a constant plus e to the minus lambda t over here, and this is supposed to be true for all time, so that means that a has to equal to bc. Or in other words, we have to say c is equal to a over b, and we already know that a over b, by physical reasoning, which the algebra will confirm if I didn't make a mistake, is also equal to omega f over g. So we know what c is in this solution of this differential equation. So that makes the constant on this side equal the constant on this side, namely 0. Go ahead, ask out loud.
I see how you get to that by putting the d equal to saying d equal to that. How else would you get the d equal to negative?
You're the straight man in the comedy show. Yes, that's what I'm saying. D equals lambda, because that's how else could we get these two sides to equal each other? Exactly. That's precisely what I'm trying to say, only I wasn't trying to say it quite yet. Okay, so now these two terms we've got to go away, but these two things have to match. The only way these two things can match is if d equals lambda. Sorry again. If b here, do it slowly. We got rid of these terms over here. We have to have that the coefficient of the exponential is the same on both sides. So d lambda has to equal to bd. we know nothing about D, it tells us that lambda is equal to B. So D is still a free constant in the solution, and this is often what happens when you solve differential equations, is that you have a free constant. But we're going to be able to figure out what that free constant is by looking at the initial conditions. So how do we figure that out? We now have our solution for the differential equation. Our solution is V equals C minus D e to the minus lambda t. Our C, we figured out, was equal to omega f over g. And then we have minus D times something, and this is e to the something or other. It was e to the a over b. It was e to the b t minus bt, and this b was a mess that we got from over here. What was the b? It was this coefficient over here. It was m0 g squared over omega f. If I did that right. Somebody can check me on that. So now we have the solution to the differential equation. It has this free constant d in it. How are we going to figure out what d is? Well, we know that at t equals 0, v is equal to 0. So what does that tell us about that d? It says that this whole expression has to equal 0 when t equals 0. It means t has to equal omega f over g. So d equals omega f over g, which then tells us that v is equal to omega f over g times the quantity 1 minus e to the minus bt, where b we figure out from that stuff over there. So now we've got v as a function of t, and we could integrate this one more time to get x as a function of t. Now that's a simple exponential expression. If we want to solve for what's the t when we get to some critical velocity, this one happens to be, usually when you see exponentials and so on, you can't invert them, or often you can't, but this happens to be one you can invert. You can take this 1 to the other side, you can take log of both sides, and you can solve for t in a logarithmic expression. Okay, so how many people actually got to the point of getting an expression that had logs in it for the t that it takes to get to a given speed? So yes, you got t equals the log of something that looks like it might be what I had on the board there, and no, you did not get that. Yes, you got it, no, you didn't. Okay, so very good. Remember, no pain, no gain. If you all got it, it would be too easy. What you're supposed to be learning is how to enjoy the struggle in this class as opposed to other classes where you're supposed to be learning a bunch of facts. Okay, so let's see what we get if we plot some of these things. I want to make this go away, hide this, stop this, make MATLAB active. So here's my attempt to use MATLAB as a graphing calculator. So this is not using MATLAB to do the integration, the summation. This is just using MATLAB to go through the results. There are a couple morals in this. One is, as you do your work, you don't want to be plugging in numbers. You want to stick with letters. On the other hand, when you stick with letters, you also don't want to go about plugging in letters into letters. If you always insist on plugging algebraic expressions in and substituting as you go, you get very complicated formulas. Whereas if you just keep the formula simple as you go, then when you do the actual plotting, say in MATLAB or calculation, you can do the substitution as you go. So for example, here, we were given that the peak power was half a horsepower, so here's a half a horsepower in watts. Everything is nicer on the computer if you just set things up in consistent units. So any numbers you put in, make sure you put them in some consistent units. Meters, kilograms, seconds are nice. Pound force, seconds, and feet are also good, or pound mass, seconds, and feet are also good. Okay, so I'm going to do MKS, which I'm sure most of you prefer. We have the mass in kilograms is 150 divided by 2.2. We have the angular velocity was given as 180 RPM. RPM is revolutions per minute. We need to multiply by 2 pi to make that radians per minute, divide by 60 to make it radians per second. We were given that the final velocity that we're interested in solving for was 20 miles per hour. We multiply by 1,600 to get that in meters per hour, divide that by 3,600 to get that into meters per second. So these were the numbers that we were given from which almost everything else follows except for the things we measure on the bike. Now in the bike, we measured all these radii. There's actually, the answer was the ratio of 3 radii. I've divided it up differently here and put the ratio of 2 radii, and I put it in the ratio of gear teeth, standard gear teeth ratios. So this is the ratio of the gear teeth on the front crank, standard. This is a standard intermediate. If you have 3 chain rings on the front of a monitored bike, this is the standard value for the intermediate one. This is a standard value for one of the small sets of gear teeth on the back, so-called R, the freewheel number of gear teeth, the rear cluster number of gear teeth. 27 is the diameter of a bike wheel in inches. Divide by 2, but this is on the bottom of the fraction, and we have to correct to get this into meters, so there's a 39.37, and this whole thing then is a gear ratio in reciprocal meters. Then we have these derived quantities. The moment that you can apply, when you're stalled, we calculated that from the peak power as proportional to the peak power divided by the peak angular velocity with this factor of 4 because the peak power occurred at halfway up. We had these quantities A and B in the differential equations, which I hope if I've done the algebra the same way just now on the board as I did before. These are the things. We have the lambda, which was B, as pointed out by the guy in the 4th row there. We have V0, which is the peak speed that you get to asymptotically is omega f over g. Now we want to plot things. We have, let's just look for 15 seconds how things go on this bike. So this is taking 1,000 points. For each of those 1,000 points, let's calculate the speed of the bike. And this is just this expression for the solution of the differential equation. And here I should have done this with C and D and written C equals D equals. It would have been even more transparent. And then we can integrate one more time that exponential, which I didn't show you on the blackboard, which gives us X. We can plot T and V. We can calculate this logarithmic expression for the final time in terms of the final velocity. This is what 7 of you or 9 of you said that you did. And then we can also plot position versus X. We run this thing, and we get, here are the 2 figures, figure 1 and figure 2. We get the velocity increasing in time in meters per second, and the distance increasing in meters. If I've done this right, it looks like a lot of meters there. Is that right? Something to check. And then we get, if we just look at the numbers that came out, we said the V final corresponding to 20 miles an hour was 8.9 meters per second, and it takes 11 seconds to get there with this particular gear ratio. So did anybody use numbers similar to mine and get an answer similar to this? Anybody use numbers similar to mine and get an answer different from this? Anybody have any thought about anything I'm saying?
Gear ratio.
How many people hear me going blah, 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 and go, what? Did he just ask a question? Okay, so you're in the neighborhood. Okay, we've got 1 minute left for questions about this code or about any of this reasoning. Don't fold your notebooks yet. Think about things. If you want, I'll post this code. Yes? Say again?
What's the 2.7 and the 39.37?
Okay, so this is the ratio of the number of teeth of the freewheel to the number of teeth in the chain wheel, and that ratio is also the ratio of the radii of those two. The third quantity is the radius of the rear wheel, which is R sub W, which was on the bottom of the fraction. So that's 1 over 27 divided by 2 in inches, because it's a 27-inch wheel, which means 27-inch diameter. And then we have to multiply by 39.37 inches per meter to get the inches to cancel and get the answer in reciprocal meters. Any other questions? Okay, just quickly, I realize today's class was fast. How many people could kind of keep up? Raise your hand. Kind of not keep up? You like a fast, dense lecture like this, or do you like the more philosophical one? Fast, dense, yes? More philosophical.